So, just a brief on relevant and irrelevant variables. These are very important in renormalization group. So, this is called renormalization operator. You can think of that the matrix is an operator. Right now it is linear, but it could be nonlinear as well. So, if I start from some parameters, then I will go to the new parameter under this operation, right. We showed that R 0 goes to R prime. Okay. So, R G is a parameter, apply R, it goes to G prime. What happens to the fixed point? If I start from fixed point, I remain there under R G. So, this property of G star is a fixed point. Now, I think I will not get into detailed discussion on this, but let us just quickly look at this stuff. So, if I at G star I will remain there, but if I start from G, then I go to G prime. Okay, that is what I am going to. So, is bit of algebra. So, I make G and G prime close to G star. So, I can do linear perturbation. So, G prime minus G star is nothing but R G minus G star, and R is a linear operator. So, linear operator, then we can write in a matrix form. So, so it has eigenvectors. It could be, right now I get 2D matrix, but it could be any dimension matrix. So, R lambda L is lambda L. So, lambda L is a eigenvalue, and this this object is eigenvector. Okay, so if I apply this so basically delta G prime, delta G I can expand as in terms of these eigenvectors. Okay. So, I will basically start from here, but I will get how this coefficient CL is changing under RG. So, the CL prime is my what happens after RG operation, which is equal to CL lambda L. Okay. So, that is what I written it here, and okay, CL prime is CL lambda L, but this is the beauty of this. So, lambda L is written as b to the power YL. Okay. This is my exponent. Okay. This is my exponent, and YL is the important coefficient. Well, eigenvalue already obtained, no, 2 minus epsilon by 3, but that is in L, not in B. So, in fact, what we got right now is already YL. So, what I had was not lambda L, but YL, and so CL is basically going as exponential YL L. Okay. Now, we will make a table. So, YL you have to look for, if I write in terms of L variable, I get YL as a eigenvalues, and if YL is greater than 0, then is relevant. That means that parameter is growing with under RG. If lambda L, sorry, this is less than 0. If lambda L is less than 0, is irrelevant. In lambda equal to 0, then it is marginal. So, it can depend sometimes, it can not depend sometime, depends on the higher order corrections. Okay. So, for the Gaussian fixed point, let us look at the parameter YR or YT. So, R is that R0 direction, YR is 2 and YU is minus epsilon. So, these are irrelevant, but YR is relevant. If a non-Gaussian fixed point, similar story, that this is relevant, but this is not relevant. Okay. So, we had the fixed point, or rather we had the RG operation, we saw how the parameters are changing with under RG, but now we got certain property near the fixed point. Okay. And now I am going to connect it to StatMech phase transition. Was it by the nonlinear part has been done in classical physics, how to analyze the matrix? Yes, no? Eigenvalues. So, dynamical systems like oscillator problem, right? So, it is very similar, I mean that same analysis. Okay. So, let us now connect it to StatMech.